Hello everyone, I'm Utkarsh Mishra and today I'm going to present our work on dynamic mirror descent based model predictive control for accelerating robot learning. In context to model free reinforcement learning, an agent interacts with the real environment, collects experience data, and learns based on the collected data. Such a framework has advantages like no model priors or knowledge about the environment is required, and because there is strong exploration, complex behaviors can be realized. However, it is typically difficult to explore in real systems, and it requires millions of interactions to learn. Recent literature have proposed solutions like model priors to collect predictive experiences and lessen model interactions and shift to hardware in-loop training. In context to model-based reinforcement learning, a two-loop approach is followed. In the outer loop, the agent learns directly on the environment, and in the inner loop, the agent directly learns on the model of the environment. Prior works like model-based policy optimization and model-based offline policy optimization have trained their policies in an offline manner based on the data collected from the environment. And works like Model Predictive Active Critic have trained their policy on both the environment and model data. We propose dynamic mirror descent model based reinforcement learning, which bridges the principles of online learning for predictive control and model based RL. We show theoretical guarantees based on regret bounds from online learning principles. We show that the maximum regret experienced in the inner loop decreases while the outer loop RL policy evolves. Further, our method incorporates adaptive planning in the inner loop, that is, the importance given to the inner loop increases as the reinforcement learning policy evolves and better approximates the model of the environment. We experience minimal interactions with the real environment, that is, 10 times less interactions than model-free reinforcement learning algorithms and 2 times lesser interactions than model-based model-free reinforcement learning algorithms, thus increasing the sample efficiency. In the outer loop, a policy is used in the actual environment and the experience collected is stored in the replay buffer DENV. Based on the data collected in DENV, the dynamics and cost models are approximated with a supervised learning strategy. We use soft actor critic, an off policy reinforcement learning algorithm, to learn from data collected in both the environment and the model. In the inner loop, we do dynamic mirror descent based model predictive control. With the current SAC policy, we collect many rollouts or many trajectories for each step horizon. Using the value function as the terminal cost, we construct the cost of a trajectory as the discounted sum of costs. And then we choose a light set of rollouts using cross entropy maximization method. Based on the selected set of rollouts, we calculate the action gradients. Now, with the action gradients, we shift the action trajectory predicted by the outer loop policy. And based on the new action trajectory or the shifted action trajectory and the dynamics and cost models approximated using the real world data, we collect new trajectories and add it to the experiences collected from the model. We compare MDemoRL against MOPAC and MBPO in OpenAI Mojoko benchmark. We get best results with nearly twice the acceleration that is achieved by prior works. We optimized the elite ratio to be used for the cross entropy maximization strategy and concluded it to be 10%. Based on the efficacy of the method, we tried direct hardware in-loop training on two-link leg manipulator with the task of foot trajectory tracking and elliptical path. The model starts with random exploration and gradually it tries learning the elliptical trajectory. Within 80 epochs, torque control learning is achieved, that is, less than 80,000 interactions. Further, it is to be noted that no filter in motor encoder readings were added. Thus, an S-step look-ahead policy optimization combined with off-policy reinforcement learning is addressed, which reduced interactions with the real environment for direct hardware experiments. For future work, we aim to explore theoretical guarantees on benefits of predictive experience in offline reinforcement learning, and typically, we want to borrow concepts from control theory so that These applications can be extended to safe autonomy. Thank you.